All right, today we're diving into a really exciting new frontier in AI. We're going to go way beyond the kind of data we're all used to, like images and text, and start to understand something much, much deeper about the world. Okay, so let's get right into it. We all know AI is great at recognizing pixels in a photo or words in a sentence. But here's the thing. The world isn't just a collection of individual objects. It's built on these incredibly complex relationships. So we're going to explore how AI is finally learning to see these higher order structures that define everything from our social circles to the physics of how a t-shirt wrinkles. The models that power so much of modern AI, things like graph neural networks or GNNs, well, they have a kind of fundamental blind spot. They see the world in pairs, right? Just one-to-one connections. But that's not how reality works. The real world, whether it's a team collaborating on a project or a molecule forming, is all about complex group interactions. So let's just break this limitation down a little bit more. Why isn't a simple web of connections really enough to capture how rich and messy the real world is? Here's a pretty simple way to picture it. A graph is absolutely fantastic at modeling a bunch of one-on-one phone calls. It can tell you who called whom, when, for how long, but it has no idea how to understand the dynamic of a group chat, or a big conference call, or even just a dinner party, where everybody's interacting with everybody else all at the same time. And this isn't just some abstract problem, right? It shows up everywhere. Think about a research paper with 3 authors. That's a single 3-way relationship. It's not just 3 separate pairs of people working together. Or what about simulating a piece of fabric in a movie or a video game? The physics isn't just about pairs of threads. It depends on the tension and the forces across whole triangles of particles. Simple graphs really struggle with that. So, to get past this, we need a whole new way of thinking. We have to move beyond just simple lines connecting dots and start seeing the bigger picture, the overall shape and structure of our data. And that requires a totally new perspective. And the key idea here comes from this really powerful field of math called topology. Now, don't let the name scare you off. At its heart, topology is just about the essential shape of stuff. It's the reason a coffee mug and a donut are basically the same thing to a topologist. They both have exactly one hole. This lets us capture the really fundamental structure of data. The holes, the connections, the empty spaces, that doesn't change even if you stretch it or squish it. And the researchers behind this whole framework put it perfectly. They said that to really truly get at the deep meaning inside complex data, you have to consider its topology. So that leads to the big question, right? If graphs aren't enough, how do we actually represent this richer structure so that an AI can make sense of it? And this brings us to the hero of our story, a really powerful and flexible new data structure that was designed for this exact problem. It's called the combinatorial complex. You see, what we really need is kind of like a Swiss Army knife for data structures. We need something that can handle those specific one-to-one connections, like a graph, but also these messy, arbitrary group interactions, like something called a hypergraph. And it has to do it all at the same time, in a way that makes sense. And that's where the combinatorial complex, or CC for short, comes in. Think of it like building with Legos, but for relationships. It starts with points, those are called 0 cells, then it connects them with lines, or 1 cells. But here's where it gets cool. It can then fill in those lines to create faces, or 2 cells. And it doesn't even stop there. It can keep going to build 3D volumes, or 3 cells, and even describe relationships in dimensions we can't even visualize. So how does the CC stack up against the other options? Well, as you can see, other structures make you choose. A cell complex gives you a nice, neat hierarchy of relationships, but it's rigid. A hypergraph gives you that awesome flexibility for group relations, but there's no hierarchy at all. The combinatorial complex is the only one that says, why not both? It gives us the structure and the flexibility. It's really the best of all worlds. So the bottom line is this. We finally have one single, unified framework that can represent pretty much any kind of discrete data you can throw at it. From simple things like text and images, all the way to insanely complex 3D meshes and dynamic social networks. Okay, so we've got our super powerful new data structure. That's the first half of the puzzle. But now for the big question. How do you actually get an AI to learn from something like this? The answer is you build a brand new kind of neural network that's designed to live right on top of this structure. And they're called, you guessed it,
combinatorial complex neural networks, or CCNNs.
And what's really cool is that building one of these CCNNs follows a pretty clear four-step blueprint. First, you define your basic things, your people, your particles, your points. Second, you build the combinatorial complex to map out all their crazy, higher-order relationships. Third, and this is super important, you define the rules for how information can travel between all the different levels of your complex. From points to lines, from lines to faces, and even back down again. And then finally, you just build the network layers that are going to learn from that information flow.
Now, the real magic, the engine that makes this whole thing go, is an operation the researchers call a push forward. But look, don't worry about the fancy name. It's just a simple rule for passing messages and combining information between the different dimensions of the data. It's how a feature on a single point can influence a feature on a line that it's a part of.
So for example, this push forward thing lets a network pool information, or basically to zoom out and see the bigger picture. It can start with all this detailed info living on the individual points, the zero cells, and then it can push that information forward to create a summary on the lines connecting them, the one cells. And then it can do it again, pushing the info from the lines onto the faces, the two cells, creating a more and more high-level view of what's going on.
And that right there, that is the secret sauce. This ability to just effortlessly move information up and down the dimensional ladder is what lets these networks think about data at every level all at once. From the tiniest local details on the points, to the regional patterns on the faces, all the way up to the global structure of the whole thing. Okay, so this is a really fascinating framework, for sure. But what about the real world? What can we actually do with all this? Let's take a look at the payoff. Well, it turns out the applications are incredibly exciting, and they're all over the place. TDL models are already being used to do super detailed 3D shape analysis, like automatically figuring out which part of a 3D model is the head, the legs, or the tail. They're being used for complex physics simulations to help discover new drugs by understanding how molecules really interact, and even to find patterns in regular old graphs that traditional GNNs just completely miss. And hey, this isn't just theory. The proof is right here in the results. The research is showing that these generalized CNCNNs can get performance that's just as good, and sometimes even better than these super specialized models that were handcrafted for just one specific task. It really proves how powerful this unified topological approach is. And that really brings us to the final big thought here. We've really just scratched the surface of a whole new way for AI to see the world, moving from simple connections to complex shapes. So you have to wonder, what doors are going to open now that machines can reason about relationships that are so much more complex than just simple pairs? What problems that we thought were impossible are suddenly, finally, within our reach?